Welcome back. So, we're going to take a bit of a detour from our pi calculations to think about how we might represent numbers, including the fractional portion of numbers, in a base other than base 10. So, this is where we ended. No, I shouldn't run that completely because it crashed my laptop last time I tried. So run that for 1,000 iterations. So you can get the basic idea. Gregory Leibniz's pi is a bit of a beast. It just runs forever to converge. But 1,000 iterations will give us the first two digits after the decimal point. Anyway, I'm used to looking at pi in base 10. I found myself wondering lately, what would it look like in a different base? Base 7, base 5, base 2, I don't know, something. But to do that, we need to figure out how to render that conversion. So, let's just look at a number for a minute. I want to know how much that can do for us. Well, no. Problem is, we're going to be looking at lots and lots of digits, and .NET's ability to keep up is going to end pretty quickly. Like most of the math functions are using doubles, and I'm going to want to eventually get out to millions of digits, or however many digits we can get a hold of. Let's start with converting integer. How do we represent an integer that was in base 10 and like base 16? Let's call it toString, and doesn't like the word base because that's a keyword. What do I want to call this thing? We'll just call it base. B. B for base. Let's say we're starting with an integer. Right line toString and 5 and base 16. How do I want to do this? We're going to try to grab the first base 16 digit in the, I don't know, the lowest value position. So just take the value mod 16, that gives a value from 0 through 15. Actually, just want to return that. So we got the number. Convert that to a character, and the way we're going to do that, if v0 is less than 10, I'm going to return the digit as a string. Otherwise, we're going to return v0 minus 10, so the number 10 becomes a 0. Convert that to a char, add whatever the values of a is gets converted to a string. So like 10, it becomes A, 15 becomes F. Now if we run this program, it'll just print out 5, because the value of 5 in base 16 is just 5. But if we print out the value of 16 in base 16, we should get 10. 15 should be F. And if we print out 0x, let's say 4A in base 16, it should print out 4A. Let's see if it does. No, I'm missing something. Okay, what am I missing? For the first one, it prints out 5. But if we come back through with a 15, 15 mod 16 is still 15. 15 minus 10 is 5. Plus A should not yield us 70. Value of A is 65. 65 plus 5 is the 70, and then it's converting the 70 to a string. That's what's going wrong. Let's change our parentheses around. Ta-da! Grabs the first digit, but for A, it's dropping the next one because we actually need a loop. So we get that, grab that first digit, the lowest value digit in the value parameter. But to grab the next digit, we take the value, divide by the base. Like if it was base 10, we divide by 10, and now the digit in the tens place becomes the ones place. If it's base 16, then a similar thing will happen, we're shifting the digits backwards. And we can't just return it now. Let's see, how do I want to print this? Properly convert the, like if it's the number 0, add the character 0, and now you have offset into the character range for that number, basically. So that'll give us a list of digits. Join those together. And that's probably reversed from what it needs to be, but I'm going to run it anyway. See, instead of 4A, it's A4. Let's see, inverts the order of elements in a sequence. Just reverse it. And then do another test here. Trying a 4-digit hexadecimal number, and there you go. So you grab the integer portion by doing the modulus followed by a division to keep pulling off the lowest value digit. How do we grab the fractional portion? I'm pretty sure what needs to happen is that it's like if it's a base 10 number, then multiplying the number by 10 would grab the first digit after the decimal point. So you'd multiply and then modulus to grab that digit. So I'm going to try to do at the whole portion, which is, first of all, let's allow this to take a decimal value. The whole portion is I'm going to go ahead and round it and squish it down to an integer. Make sure that still works. No, that doesn't still work, because that needs to be on the condition on the while loop. Alright, so that still works. If I was doing 10.5, let's keep it in base 10. Right now, I would expect it to just print out the number 10 instead of 1A. Why is it printing out 1A? Oh, got modulus B, not modulus 16. There, prints out a 10. We need to grab the fractional port. Sure. The value minus the whole should carve off the fractional portion. The fractional portion doesn't equal 0, multiply by the base, do the modulus, and then should be the same thing of just pull those digits off. Keep going until we have a 0 for the fractional portion. Something for the decimal point, and then only process the fractional portion if there is a fractional portion. Now theoretically, that should give us a 10.5 at the end. Or an overflow. Line 59. value of the fractional portion at that point. On the first iteration, it's 0.5 multiplied by 10, then it's 5. Oh. And then we need to carve off that fractional, carve off the whole number. So we take the whatever the value of frac is, which should be something like 5.0, subtract the integer portion that we just calculated, and that should just leave us the fractional bit, I think. There you go, 5.10. No, it should be 10.5. Okay, let's think. We reverse the digits right after we are done with the whole portion. And there we go, 10.5. That's what we want. Let's try a couple more. I'm not ready to try negative numbers, but try those. Okay, so far so good. Now we're going to try something a little different. Let's look at the value of 1/3 as a decimal. That's the expected value, 0.3 forever. Let's try that same value in a couple of other pieces. Base 3, base 5, base 7. Let's just see what it does. It pings before it even outputs the first value, because it never runs out of 3s on that fractional portion. Let's write that out. Whatever digit it's finding. Oh my, that was ugly. Alright, that's different. Each digit is a decimal value. The base is an integer. We need to compress that to an integer. Now it's given us integer digits, but it's doing it forever. So Now it can only go as long as the counter is greater than 0. At some point, it has to give up. Okay, that's looking more useful. So, 1/3 in base 3, base 5, and base 7. Still an approximation, because base 1/3 seems just want to go on forever. Now what I'm wondering though is, what if we took something like the value of pi and converted its base? I'm going to dump it out in base 10 first, just to make sure my function's doing what I think it should be doing. And then we're going to try a couple of other bases. Just want to see what it looks like. And there you go. It has a different appearance. I'm not sure what we can do with it yet. Base 2, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 1. I wonder what would happen if that kept going. We can't know the number of digits that we have. Of course, we can extend the counter. Let it go out to 100. And what I'm wondering is if you look at pi in a different base, do different patterns emerge? I don't know, it's possible this has already been researched, but I've never researched it before, so it's interesting. Zero, 0, 1, 0, 0, 1, 0, 0, 0, 0, 1, bunch of ones. So the first line is base 2, second line, this line here is base 3. After that is base 5, 7, 9, 11, and 13. It's where you start seeing letters because we have digits past 9. And I think I'm going to stop there for now. This appears to be working. I'm wanting to do a couple of other things with these digit streams. I think in order to get a good representation, I'm going to have to do something with the, like, there's a system numerics big integer class for if you want to have an arbitrary, really large signed integer. There's a couple of implementations I've seen of a big decimal class for arbitrarily large fractional numbers. And I need to grab an implementation of that, and then I think we're going to play with some sound generators. So, something to look forward to next time. And see you later. Thanks for watching.